incremental structure from motion and some challenges of structure from motion. So let's first recap structure from motion. So the structure from motion, so this is the entire pipeline of multiple geometry theory. We've all learned this. And structure from motion, it is a kind of practical algorithm. It does not require camera calibration. Of course, we can use camera calibration. It is good, but it is not necessary. If we have just multiple images, then it finds correspondences between images by image matching algorithm that we learned in lecture 3. And epipolar geometry is used to get some camera parameter between frames. And then we can lift them to the 3D space using triangulation. And this entire pipeline is called structure from motion, getting 3D geometry and camera parameters at once from a video. That is the structure from motion. And this is just the output of structure from motion. And we learned, so there are ambiguities in structure from motion. So because we do not have 3D measurement, that makes all the ambiguity. In addition, we do not have enough observation, as we are trying to get P and X camera parameter and 3D points at the same time from only 2D observation. That is ill-posed problem. So mathematically, here's the ambiguity. For example, scale. If we multiply entire scene, large X, by some factor K, and at the same time scale the camera matrices by the factor of 1 divided by K, the projections of the scene point remain exactly the same. That makes scale ambiguity. And in general, if we transform the scene using a transformation Q and apply the inverse transformation to the camera matrices, then the image observation do not change. So we have affine ambiguity as well, transformation Q. So these are projective ambiguity, and this is affine ambiguity. We learned this kind of transformation in lecture 2, right? Projective transformation, affine transformation, similarity transformation. Q can be any transformation matrix, and then depending on what Q is, we might have some ambiguities. These are some examples: projective ambiguity, affine ambiguity, similarity ambiguity. And then there are two kinds of structure from motion. One is affine structure from motion, and the second one is perspective structure from motion. Affine SfM approximate cameras as parallel projection without perspective effect. That means we approximate camera as a affine transformation. Originally, it should be perspective projection, arbitrarily 4x4 matrix, but we are trying to elevate the ambiguity of SfM by approximating camera as a parallel projection. It is only valid when the scene is far away. And projective SfM uses standard pinhole camera with perspective effects. So affine SfM, it tries to reduce the ambiguity by approximating camera as the affine transformation matrix. And these are, so there's a recap: affine, projective, and these are some degree of freedom in 3D transformation. And projection matrix is just a multiplication of extrinsic and intrinsic camera parameters. And so we tried SVD, right? We tried SVD to decompose measurement matrix D, just 2D coordinate across multiple images. We can decompose the matrix into 3 items, and then there can be many solutions. Like here, Q can be arbitrarily matrix. So this mathematically shows where the ambiguity comes from. And the affine SfM tries to relieve this ambiguity by approximating camera as a affine projection. And projective SfM, basically strategy is almost the same. Just trying to get camera parameter and 3D point at the same time from 2D measurement. That is, this kind of strategy is almost the same. But the difference is that we are trying to use projective transformation, original projective transformation when modeling camera without approximating camera as a affine transformation matrix. Yes, and there are in perspective SfM, there are global SfM and incremental SfM. In last class, we learned global SfM, right? Global SfM, it uses all pairwise relative poses together and solve the entire camera graph at once. That is the reason why we have global here. It uses all the pairwise relative poses together. Incremental, it is the opposite thing. Instead of using all pairwise relative poses together, you start from a small set of images, then add cameras progressively, a camera one by one, and expand the reconstruction gradually. So global structure from motion, as I said, here is just image matching, right? We learn SIFT and we can get image matching, and then we have multiple relative camera rotation and translation between frames, right? So here we have input is many noisy relative rotation. Relative rotation means rotation, 3D camera relative rotation between images. We only have relative rotation. But the problem is that they are inconsistent. This shows the example. R12 multiplied by R23 should be R13. Relative rotation between camera 1 and 2, and relative rotation between camera 2 and 3. If we multiply them together, then we should get rotation between camera 1 and camera 3, in theory. But unfortunately, we have lots of noisy estimations, noise optimization. So this does not hold. This does not always hold. So we need to find global rotation that best satisfies all relations. Translation as well. We only have local relative translation between images, but what we want is camera position, not relative between images, just global absolute camera position in world coordinate system. That is what we need. So to get this, global SfM tries to use all pairwise relative camera poses together, and then from global SfM's initial result, we can try bundle adjustment. We learn bundle adjustment, right? It just tries to adjust camera parameter and 3D geometry together by minimizing reprojection error. During bundle adjustment, we can use RANSEC to make it more robust to outliers. So anyway, that is global structure from motion that we learned in previous class. The good point is that less drift because the solution is globally consistent, less sensitive to initialization, scale better for large internet photo collections. But the drawback is that sensitive to noise and relative pose estimates and non-convex global optimization can be tricky. So that today we learn incremental structure from motion. So incremental structure from motion, as I said, it tries to use only a subset of images at the first, and then gradually add one by one images so that it can improve the reconstruction quality gradually. That is the incremental structure from motion. So automatically select initial pair of images. After we have image matching, using SIFT, we can use automatically select initial pairs of images. So how can we pick initial pairs? So there are several things that we need to consider. So we want to pair with many matches. That is definite, right? We want pair with many matches so that we can lift the point to the 3D space better. But so there are two things we need to consider. The first one is lots of match. Why there should be new line here. Large baseline, lots of matches. So there are two things, image matching and small baseline. So we learn baseline. Remember what is baseline? In epipolar geometry, we learn baseline is a distance between camera. So there is a camera 1, this is camera 2, and it is shoot ray. There's a point, and this is the epipolar plane. This is the epipolar plane. And then this one is baseline. This is camera 1, this is camera 2, and this is baseline. Line between cameras. So we need to consider both number of matches and the length of baseline. So here, these two images have lots of matches, right? They look almost the same. So they have lots of matches. But the problem is that they have small baseline. Small baseline means, so these two images are taken from different cameras, but they look almost the same. That means the length of baseline is very short, right? Actually, if length of baseline is too small, it is not good actually. The extreme case of small baseline is just taking images from one camera. But we know, right? We know that if we take images only with one camera, we cannot lift them to 3D space because of depth and scale ambiguity. So we need some length of baseline, not very small, but unfortunately in this case, they have lots of matches. They look almost the same, so they have lots of matches, but they look almost the same. That means the length of baseline, length of line between camera is too short. So this is not a good pair actually. How about this? This one. No, this one is not. Why they? Sorry. Oh. Okay. Okay, very few matches. So these two images, they have large baseline. That means these two images are also taken from different cameras. But so as we can see, these two images are very different. So they have large baseline. The line between two camera, length of such line is very large. It is large, but it have too few matches. They look very different. So they might have too few matches. That is not a good actually. So this is the optimal setting. Enough length of baseline and lots of matches. That provides us 3D information, and matching is enough. So that this is the good combination. So we need to pick initial pair with enough number of match and enough length of baseline. That is kind of heuristic. How can we define what is enough number of matches and what is enough length of baseline? That is depends on your algorithm. That is kind of heuristic. But we need to consider both things when picking initial pair for incremental structure from motion. The number of match should be enough, and the length of baseline should be enough. The number of match then needs to be enough so that we can lift many points to 3D space stably. And large baseline, it is necessary to get some 3D information. The extreme case of small baseline is just taking image from a single camera, right? Then in that case, the length of baseline should be 0. But that is not desirable, right? We need images from different viewpoints. So that means we need some enough length of baseline. So we need to consider two things: the number of matches and length of baseline when picking initial pair of incremental structure from motion. And pick a pair of images with lots of inliers and preferably good EXI feed. So EXIF is a kind of metadata. Metadata. It provides camera intrinsic or GPS, all the thing. Camera intrinsic and GPS. If we can utilize EXIF data, that is definitely good. But in many images, especially images on the web, they do not have metadata. They just have RGB values. But if we can use this one, then we actually have lots of valuable information, camera intrinsic and GPS. So anyway, initialize the intrinsic cameras from EXIF if we have EXIF, and estimate extrinsic parameters using 5-point algorithm. We learned this in epipolar geometry. and use triangulation to initialize model point. If we do not have EXIF, we can still get intrinsic up to scale, right? Because we can use epipolar geometry, right? We can use epipolar geometry to get all the intrinsic and extrinsic. But if we can use EXIF data, then we can use camera intrinsic from it, and then we can just use PMP model. We learn PMP, right? PMP algorithm to get extrinsic. PMP assume we have intrinsic, right? And that is the initial pair of incremental structure from motion. And remaining images, there's just a while loop. While remaining images exist, find an image with many feature matches with images in the model, and run ransack on feature matches to register new image to model, triangulate new points, perform bundle adjustment to re-optimize everything. Optionally, they're just optionally align with GPS from EXIF data or ground control point, just optional. If we have this kind of data, we can utilize them, but don't worry, if we do not have, we can just skip it. We can just focus on these 4 steps. And these all things, we learned this, right? Find an image match. We learned this image matching, lecture 3, remember? And run ransack on feature matches, register new images to model. We learned this in bundle adjustment, triangulation, bundle adjustment, we optimize everything. We keep repeat this while remaining images exist. So that is the incremental structural motion. I guess not very complicated, just a combination of what we learned so far. Image matching, triangulation, bundle adjustment, and here epipolar geometry. In the first stage, we need to use epipolar geometry or camera calibration, assuming we have EXIF data. And remaining thing, image matching, triangulation, bundle adjustment. Is it clear? Is it good? And next best view problem. So here, find an image with many features. That is a little bit ambiguous, and that is actually next best view problem. What is next best view? Let's say we have images, image 1, image 2. We have images, our model. And in database, we have lots of images. Image 1, image 2, image 3, image n. We need to get images from our database in our model. So how can we pick an image with best view? The choice of next view impacts reconstruction quality, right? Because as I said, we need to consider this kind of thing. There should be enough number of matches, and there should be baseline length should be enough. So almost identical view, as I said, high uncertainty in triangulation. It does not have any 3D information, so it makes triangulation very uncertain. And very different view, low overlap and high camera uncertainty. Too large baseline between camera that makes this kind of low overlap and high camera uncertainty. And single bad choice may impact whole reconstruction because the incremental SfM is a kind of progressive algorithm. Progressive, autoregressive, or anything, gradual algorithm, anything. So global SfM, it tries to use all the pairs all together. That is not a progressive algorithm, but incremental SfM, it just iteratively get images from database and gradually improve the reconstruction quality. So single bad choice may impact the whole reconstruction. So we need to be careful when choosing next best view from our database, this database. So these are just a popular next best view method. Choose views with seeing the most triangulated point, minimize reconstruction uncertainty, depending on of your number of observations, distribution images. Actually, one of the most popular next best view method is, assuming we have video, then the most popular next best view method is just getting next frame from video, because if we take a video, then adjacent frames might have very similar images, so they have lots of matches. unless the camera is moving very slow, baseline between adjacent frame might be enough. That is our assumption. So that is one of the most popular next best view method. Very simple, but work in general. Unless camera is moving too slow. If camera is moving too slow, then length of baseline is too small, right? Then that does not provide enough 3D information. Of course, if camera moving too fast, then we cannot get enough number match. So camera should move properly, not too slow, not too fast. But it moves in reasonable speed, then we can get frames from next time step, adjacent time step. That can be good next best view candidates. And these are output of structure from motion, incremental structure from motion. Just capturing videos of some landmark. These are some famous landmarks, right? And then we can get some sparse point cloud from without any camera calibration, just taking video, then we can get 3D sparse point from structure from motion. And here, the visualization here, these are just visualized cameras. This is visualized cameras here, just cameras. Here, camera is, the camera is moving in this direction, seeing this direction. So these are all cameras. These black things are all cameras. And these points are from structure from motion. And challenges and application. Actually, there are some degenerate configurations like homographies. If points are on the same plane, that is actually applicable to triangulation, right? If all points are on the same plane, then it might be some ambiguous filtering out incorrect matches, dealing with repetition and symmetries. So first one is it is about matching. If the structure has repetitive patterns, they might make image matching not very good. We've actually learned this in SIFT, right? If we have repetitive patterns, let's say, so this one, as SIFT is a local pattern, SIFT is a local patch-based feature extraction, right? That means, for example, this patch and this patch might look almost the same, right? This patch, right? This one, this one, this one, this one, 1, 2. There can be, one matching between 1, 3, 1, 4, 2, 3, 2, 4, because they look almost the same. SIFT is just a local feature extraction. So if image matching fails because of this kind of repetitive structure, then a structure from motion might be messed up. So we need to use it's actually advanced feature extraction based on local and at the same time global patterns. This one is almost the same. If the image matching fails, then there's no way to recover actually. If image matching fails, then there's no way to recover. So camera should move in this direction, but camera drift in some weird direction. And as we learned, this kind of structure from motion is based on accumulating. Accumulating means we have images, image 1, image 2, image 3, and we can get relative rotation translation between relative rotation and translation of camera between images. But what we want is this is world coordinate system. What we want is rotation with respect to world coordinate system, not relative between images. What we want is just a rotation with respect to this fixed canonical coordinate system. What we want is not relative rotation between images. So to get this global structure from motion used rotation, translation, averaging, and incremental structure from motion. Also, we need to convert all the relative rotation to the world coordinate system rotation and translation. But incremental as well. If we gradually images like this, then if something bad happened in this chain, in this stage, then the followed images might be messed up. Follow image might be messed up. So error could be accumulated. So that is another some kind of problem of current structure from motion pipeline. So we need to consider both relative and global things at the same time. And these are just now let me introduce some applications of structure from motion. I'm not sure you've heard SLAM. SLAM is a simultaneous localization and mapping. It is used in robotics or self-driving car. Assuming we do not have, assuming we don't have any map, we do not have any 3D scene information, but if robot vacuum cleaner, if we put our robot vacuum cleaner in our apartment, then it tries to draw some map, right? There is a laundry room, there is a bedroom, or this is any room, so that it tries to draw a map and it tries to find where it is. Am I in bathroom? Am I in a laundry room? It tries to localize itself. That is SLAM actually. Doing localization and mapping at the same time. This is very similar to structure from motion actually. In structure from motion, we try to get camera parameter and 3D geometry at the same time. This is almost the same actually. If we get camera parameter, then that is localizing ourselves in world coordinate system. Localizing camera in world coordinate system. At the same time, we try to get 3D geometry from images. So structure from motion SLAM is very similar, but usually SLAM refers to online algorithm. Online means images is keep streamed. That is difference. SLAM, it assumes some online setting. SfM, it often assumes offline setting, assuming we have all the entire images. Let's say we have entire images, then algorithm start with entire images. But on SLAM, it assumes some online streaming case. Images keep streamed in real world. But basically these are two very similar, SLAM and SfM. Visual SLAM, free SLAM. So here is the continuous visual input from sensor over time. SLAM, it assumes continuous visual input from sensor over time. But structure from motion, people often assume we already have entire images. That is some difference. And give rise to problems such as look closer. Often the goal is to be online, real time, as I said. But basically, the strategies and what the algorithm tries to get is almost the same. Just localizing itself and getting map, or getting camera parameter in world coordinate system and getting 3D geometry at the same time, only based on 2D observation. So their goal and strategy is almost the same, but then just specific use case is a little bit different. SLAM assumes online, real-time, continuous visual input from sensor, while structure from motion, it does not need to be online. It's often offline or not real time. And we assume images are already ready. And structure from motion, it is still widely used these days. Actually, CoLMAP is from CPR 2016. So I'm not sure, maybe some of you guys heard 3D Gaussian splatting. 3D Gaussian splatting requires input from CoLMAP. CoLMAP. If we run CoLMAP, then we have structure from motion output, sparse point cloud, and this output becomes input of 3D Gaussian splatting, so that we can get more dense 3D reconstruction. That means CoLMAP or structure from motion is still widely used these days. We will learn this later. And there are many applications: 3D modeling, serving, robot navigation, map making, virtual augmented reality, visual effects. A very important piece in multi-geometry theory and still widely used This one as well, it needs to look, it is almost the same as SLAM, right? It tries to localize itself based on 2D observation. We scan ourselves with our mobile phone, scan surrounding with our mobile phone, and then tries to get its position on the planet. So we have special ordering, images and 2D feature correspondences. We have 2D observation, and then 3D points and camera poses, then 3D model generation. So I guess up to here is structure from motion. And up to here is multi-view stereo. We will learn this today. So from images, images from different viewpoints, we can get 3D points and camera poses at the same time. That is, structure from motion. And here dense. Multi-view stereo, it tries to get dense 3D. We only have this kind of very sparse point, right? We only have this kind of sparse point. Where is it? Very sparse point. Sparse means most of the points are zero. We do not have many points. The opposite meaning of dense. We have very sparse point from structure from motion. But dense, the goal of MVS is getting dense 3D reconstruction. So anyway, this is the end of structure from motion. And any questions you have about the structure from motion? No question? And let's continue multiple stereo. This is the last slide before midterm. And midterm will include from lecture 1 to lecture 9 until multiple stereo. This is the end, last lecture slide before midterm exam. And I guess today we will cover here, maybe. So I've just introduced the difference between structure from motion and MVS, right? Let me clarify difference more. So structure from motion, it estimates camera poses, produce sparse point cloud, provides skeleton of the reconstruction from only 2D observations. So the important thing is the sparse. Sparse means it is not dense. The reason is that we actually only lift matched point. If we do not have, there can be many pixels in images, but images without matched result, they are not lifted to 3D space. That is the reason why we only have sparse point clouds from structure from motion. We only lift matched point to 3D space. But in contrast, MVS tries to reconstruct entire dense full 3D surface from images. That is the multi-view stereo. Takes SfM camera poses as input. So that means MVS require camera calibration result. It might have scale ambiguity or anything, but it needs to get camera poses as input and produce dense point cloud. Dense point cloud, depth map, mesh, recover fine-grained surface geometry. Fine-grained means very detailed surface. So we see this kind of structure from motion, very sparse point, because we only lift matched point among many pixels and images. We only lift matched point to the 3D space. That is the reason why we only have sparse point cloud from structure from motion. But the MVS, it tries to get very dense point cloud, fine-grained surface geometry. That is the MVS. So here pipeline. We first perform SfM to get sparse point cloud and camera poses. And then we get MVS multiple stereo to get dense point cloud, mesh, surface geometry. And actually mesh reconstruction could be included in MVS. We haven't learned mesh. We will learn mesh after midterm. But let me briefly introduce what is mesh. Mesh is like just surface of. If you're familiar with some computer graphics movie or game, you might have heard polygon. Polygon is mesh. What is the so let's say we have bottle. We have bottle here. We have bottle. One way to represent this 3D bottle is just a set of points, as we see in structure from motion. Just set of many points, right? But another way is that we can approximate bottle as a combination of polygon. No, this is not good. But we have mobile phone. Let's say we have mobile phone. We'd like to approximate mobile phone as a combination of many triangle polygons. We can approximate mobile phone as a combination of triangle. So this is the mesh, just a set of triangle polygon. So it tries to only get surface of some object. We will learn this detail after midterm, but I'd like to just briefly introduce what is mesh. Mesh texturing. Texturing means so far we've only covered geometry without any color texture. But in full 3D geometry, full 3D reconstruction, we'd like to get texture as well. So texturing should be included in the entire pipeline. So this is the structure from motion result. From multiple images, input these multiple images, and output this camera parameter and sparse points, only for matched point. That is the reason why we only have sparse points. As you can see, we have very sparse point. This only few points, and there are many camera poses. We covered camera poses. That is the output of structure from motion, and these are output of MVS, much more dense, right? Fine grain wrinkle of clothes, facial expression, and here overall shape of surface of some sculpture. All things need to be included in MVS. So input these multiple images and camera parameter. Camera parameter can be obtained from either structure from motion or camera calibration. If we just use videos, if we take just a video with our mobile phone, then let's say we do not have access to checkerboard, then camera parameter should be from SfM. We can get camera parameter up to scale. But if we have some kind of multi-view capture studio, like if we have some studio and we can have access to checkerboard, we can do camera calibration before data capture, then we can get camera parameters from camera calibration, right? So camera parameter can be obtained from either structure from motion or camera calibration. Output is dense points and surface. Here, can you see difference? These are just a set of sparse points, but here we have full surface geometry with very detailed wrinkles, facial expression, hair, and over shape of sculpture. All the things should be included in MVS. In other words, it is called 3D reconstruction. This is very famous field, very important field in computer vision, 3D reconstruction. So structure from motion can be performed to do 3D reconstruction, to get initial camera parameter, to get initial 3D geometry. But the MVS, in other words, 3D reconstruction, the goal is to get very dense, detailed 3D surface of all from all viewpoint. That is the MVS. In other words, we call this 3D reconstruction. So this is the entire pipeline. Actually, this entire pipeline is multi-view stereo. Entire pipeline is a multi-view geometry theory, but the entire pipeline is multi-view stereo. We get, if we have checkerboard, then we can do the camera calibration, right? If we do not have checkerboard, then we can get camera parameter from SfM, anything. So we can have camera parameter from either from checkerboard or SfM, anything is okay. And then we have multiple images. The input are two inputs, multiple images and camera parameter. Then we have matching, and do something triangulation to get full dense 3D surface. That is the 3D reconstruction of multi-view stereo. The problem formulation, given several images of same object or scene, compute the representation of its 3D shape. Here you can see it's quite dense, very detailed, normal. All the detailed line is preserved in 3D reconstruction. And we can use some setup. We can use multi-view setup. So these are some specialized cameras to do multi-view stereo. This point Grace Bumblebee, point Grace Profusion. These are some specialized cameras to do multi-view stereo. And this CMU's Panoptic Studio, or this kind of, these days many institutions have this kind of multi-view stereo. People just build some hemisphere capture studio and then install cameras uniformly in hemisphere studio. Meta has it. I guess many companies already has this kind of capture studio. Anyway, this kind of capture studio, they just use regular camera. Just regular camera, like a 4K camera. They install like a 100 4K camera. They synchronize them, they calibrate them to build this kind of capture studio. So anyway, we can use this kind of specialized cameras to do the multi-view stereo, or we can build this kind of hemisphere capture studio with regular cameras, many regular cameras, to do multi-view stereo. Of course, this capture studio, building this will take lots of money. I guess this is just from Google Earth. Have you visited Google Earth? We can look around any places on our planet. This is based on multi-view stereo. We can see lots of detailed rendering, detailed geometry images, right? That is based on multi-view stereo. Or in some museum website, we can look around many sculpture, right? Many landmark. That is also based on multi-view stereo. People pre-scan some landmark with multiple cameras and then lift them to 3D space and then let people rotate it on the virtual space. This one as well. Can you see these cameras? These are just regular cameras, and these are from Capture Studio. People build Hemisphere Studio, and they install regular cameras. Synchronization sounds a little bit trivial, but synchronizing and calibrate them all together like a 100 camera is not very trivial. Actually, it's very difficult. And throughput from 100 camera, let's say we have 100 camera and resolution is 4K and we have 90 frames per sec. It makes huge throughput, and handling this huge throughput is also technically very difficult. And so people, to build this kind of capture studio, we need to purchase lots of cameras. At the same time, we need to hire expert level engineers to handle this kind of huge throughput. 100 cameras, 4K resolution, and 90 frames per sec. That makes huge throughput. And then we need to synchronize them. Synchronize them means they need to capture images at the same time, right? And they need to be calibrated. So calibration is also very difficult and very sensitive to camera calibration, actually. So for every capture, we need to calibrate cameras again, because the humidity or temperature of Capture Studio might make camera calibration a little bit different. So that for every capture, we need to calibrate cameras. That makes very annoying, right? Very annoying. So, all the things that we can change viewpoint, that is for multi-view stereo. That is 3D reconstruction with dense textured color. Structure from motion, it only has sparse point, but if we can rotate some images, free viewpoint videos, they are also from multi-view stereo. So I hope you are familiar with, you get difference between structure from motion and multi-view stereo. This stereo SfM is just for sparse point, and MVS is trying to get dense point. And let me introduce simple approach for MVS. So the technical stuff, we already learned all the technical stuff, and this is just the application of what we learned so far, like image matching, calibration, or anything, triangulation. So let's say there's the reference view and neighbor views. Neighbor view, assuming as we know camera parameter, then we know what are neighbor views, right? Based on camera rotation and translation, camera position. And then we can draw graph, depth and error. Here depth is the depth of this camera coordinate system. So this is z-axis. If we increase depth, okay. So yes, we increase depth, the error becomes lower and lower. So this is the optimal point, lowest error. So here we try different depths in this coordinate system. We try depths in different depths, and then measure error, reproduction error, and then in this manner we try different depths and then measure errors. So we can repeat this. In this manner, we solve a depth map over the whole reference view. For each pixel, of course, we can use parallel computation. To calculate this kind of errors. We choose to measure error and depths for all pixels at the same time in a parallel way. Anyway, we just measure error and depths and pick depths whose error is minimal. So in this manner, we can solve a depth map over the whole reference view. Depth map is, I guess we learned depth map, but depth map is like it's just image, height and width, but one channel, and for each pixel, the value is just a depth value. Pixel value is depth. Depth is a distance between camera and 3D point, right, in z-axis. So it looks grayscale. So the dark means depth is small, and bright, depth is high, right? So we can get depth map for each reference view, right? That is the start of the simple multi-view stereo. The basic idea is just measure error for different depth values, and then we pick a depth whose error is the minimal, so that we can get depth map for all reference view, and then later we can combine depth map from multiple viewpoint to the 3D space. That is the very simple approach for MVS. Here we have, triangulation, reproduction error, all those stuff, image matching, all those stuff we learned so far, right? Just the application of what we learned so far. So you can match window using more than one neighbor given a stronger match signal. What this means is that we can use multiple images. Here we have multi-view stereo, not two-view stereo. We have multi-view stereo, so that we can use multiple images. So we can use more than one neighbor given a stronger match signal. And if you have lots of potential neighbors, you can choose best subset of neighbors to match per reference image. Can reconstruct depth map for each reference frame. That is what we've seen from this slide. And then we merge them into complete 3D model. We can get depth map for each images, and then we can lift the depth map to the 3D space, and then we can get full 3D model. And this is a little bit similar to what we've learned in structure from motion, baseline. So we need to be careful about the baseline actually when choosing the when doing the multi-view stereo. So this is the width of a pixel, a single pixel. If large baseline means the cameras are far apart. The distance between cameras is a little bit long. Small baseline means distance between cameras is a little bit short. If large baseline, in case large baseline, large baseline gives enough 3D information. It is good, but as I said, if baseline is too large, it is difficult to search, difficult to find matching point, right? Images are too different if baseline is too large. If baseline is too small, large depth error because we do not have enough 3D information. The extreme case of small baseline is just taking image with a single camera. Extreme case of large baseline is taking images with totally different viewpoint without any overlap. So so we need kind of enough length of baseline. And this shows the graph, multiple baseline stereo. For short baseline, estimated depth will be less precise due to narrow triangulation, right? If short baseline, they do not have enough 3D information. And this is larger baseline. They have enough 3D information, but they need to search larger area in second image. When finding matching point, it is a little bit difficult to find enough number of matching between different images. So that means large baseline is consistent with the previous slide, right? For large baseline, it is a little bit hard to find good matching. For short baseline, we can find good matching, but they provide not enough 3D information. So we need enough length of baseline between cameras. So basic approach is, so let's say we choose a reference view, and then we can use any stereo algorithm, but when choosing next best view, we can replace two views SSD, sum of difference, with sum of difference. So sum of difference, we learned this epipolar geometry to get, or image matching to get difference between local patches, right? But sum of SSD, SSSD, we now will try over multiple baselines. That is the reason why we have multi-baseline stereo. So we have, in MVS, we have lots of cameras, right? We have lots of images from different cameras. Multi-baseline stereo means we try different cameras, try different cameras. So replace two view SSD with sum of SSD over all baseline. So let's say we pick this image as a reference view, and then we compare, we get SSD from all the remaining viewpoints over all baselines. And SSD, the SSD value are computed for first for each pair of stereo image, and then added all together from multiple stereo pairs. So limitation is that, this kind of basic approach, limitation is that we have only depth map, right? What we have so far is just a depth map. We just use this kind of depth map. We just compute SSD for remaining all the viewpoint, and then get depth value for each pixel. That is what we get from this MVS, right? So we have only depth map, but depth map is not 3D model. Depth map is a 2.5D. Depth map does not provide, for example, if there is a human and there is a camera here, and then the depth map might look like this, but it only provides depth value from visible point. Depth map does not provide information from invisible point, like a back of the person. Let's say this is the front part. Depth map does not provide back part of this human, right? So depth map is not full 3D information, so we need to combine them together later to get full 3D model. But this kind of basic stereo approach, it only gives us depth map, and that is a limitation. And it won't work for widely distributed views. I mean, if the overlap is very small, I mean, widely distributed view, they have small overlap, so that it won't work. And I introduced sum of SST here, right? So SST, I guess we learned this. Some SST is just a L2 difference between point, or we can use SAD, sum of absolute difference, or ZNCC, zero mean normalized cross correlation. Just normalize each local point or local patch with the translation and standard deviation. We normalize them together and then calculate difference between them. The advantage of ZNCC is that it is robust to illumination and contrast variations. If let's say we have two local patches, and this is very bright, they have the same pattern, but very dark. If we just use SST or SAD, this might, although they have similar geometry structure, these two lines, if we use SST or SAD, their error might be very huge because this pattern is bright and this is very dark. But then if we use DNCC, then we can normalize center and we can normalize standard deviation as well, so that these two patches might have high ZNCC, right? So that is the good point of ZNCC. And the problem is that visibility. I introduced this kind of visibility briefly here. For some, images or depth map, they just 2D or 2.5D representation, so that they do not have full 3D information. That means for some point, a certain point might be visible to some viewpoint, but a certain point might not visible to some cameras. That is the problem. So here we have multiple graphs. If we have this, these are just this. So let's ignore the blue part. Let's ignore this blue part. Then there's no problem, because as you can see, this is the depth x-axis. So y-axis is SST, and for all graph, x-axis is depth. As you can see, if we change depth, then we can get let's ignore blue part, then we can get some depth whose error is very small. If we only consider black part, then we can get depth value whose error is very small. And then we can just use all these depth values to get good 3D reconstruction, good MVS. That is no problem. But the problem is that for some viewpoint, certain points are not visible, so the graph might look like blue curve, right? If we have black curve, there's no problem. But if some points are not visible, or many points are not visible to some viewpoint, then we might have this kind of blue curve. If we have blue curve, then there's a problem. Because blue curve, as you can see here, this blue curve, they do not have depth value whose error is very small. Error of all entire depths is very large, right? If we consider blue curve, this one as well, we do not have depth value whose error is small. This one as well. We do not have depth value whose error is very small. So if we consider blue parts, then if many points are not visible to some cameras, then blue curve might happen. And if blue curve happen, then MVS quality is very bad actually. So we need to consider visibility of many points. And solution to consider visibility is, as I said, match only nearby photos. They're very simple but effective. Do not use cameras with very different rotation, very different translation. Just use images, nearby images. As we know, camera rotation, camera translation, the assumption of MVS is that we already know camera parameters. Then we can compute rotation and position of cameras. And then based on such kind of camera position and rotation, we can get images, only nearby images, right? It is safe to use only nearby images because very different rotation, very different position camera, they might produce very different images, and visibility of point might be very different across different cameras. So this kind of blue curve might happen if we do not consider visibility. So to consider visibility, we need to use only nearby photos. And this shows visibility. How can we get visibility? Visibility means whether this point is visible to a certain camera or not. For visibility, it assumes known scene. If we know 3D geometry, then there's no problem. We haven't learned rasterization, but rasterization is like just rendering. Let's say we have a 3D human, and we can render this human to this image. Camera is looking here. Then rendering engine, as we have, the front part of human might be rendered, but the back part of human might not be rendered because of rasterization. So that if we know scene, there's no problem. But the problem is that if we do not know scene, if we do not know 3D scene, if we do not know 3D structure of the object, then maybe we can consider point with a large error invisible, or or we can use images from close cameras. Those are the things that we can use to get visibility. If we do not know 3D scenes, there is no way to exactly know visibility of points. Just to consider point with large errors invisible, or we can use images from nearby cameras. That is what we can do to consider visibility. We will study advanced one next time. And let me. So actually we have